Hi all, I'm Mrigank and with my friend Sahil, I'll be presenting just one more paradox today to all of you.
Let's play a game.
In fact, let's gamble. In this gamble, we'll give you rupees 100 to start with, and then we'll ask you to toss a coin. At every heads, you will get a gain of 80% on your entire sum, but on every tails, you will lose half of your money. And you can choose toss the coin every time as you wish.
Let's analyze the game. Provided a very large number of people who you want to know, on an average, the average gain among these people, and in our particular case, 0.15 is the average gain on each toss, which is a positive. This seems a very good deal, like a fair game to play, like you want to toss again and again.
So, would you play this game? Do you think this game gives you a fair chance to make money? But before that, should you play this game? Is the question. And we'll soon see that.
So consider a game with 6 coin tosses, and we have 6 combination of heads and tails here. The distribution starts from 6 heads, 0 tail to 0 heads, 6 tails, and here by frequency we mean the number of ways by which we can reach that particular state, and the final amount is the amount at which you will reach with that particular set of combination of heads and tails. Let us visualize this particular wealth versus number of toss graph where we start with rupee 100 and at first trial we reach either at 180 or at 90. After that from 180 we can either reach to 90 or 362. Similarly from 50 to 90 or 25. Similarly from 25 to this 12.5 or 180 to 324. And you can clearly see here the one of the line looks similar to an exponential curve. So the average amount at the end is rupee 231. You can easily calculate it and seems like a very good deal. Like you started with rupee 100 and on an average, the average amount at the very end should be rupee 231. So you should have with at least on an average the amount of rupee 231. Most of the people lose their money.
Yeah, so we saw that even though the average amount was much more than what we began with, most people end up losing their money. So what went wrong there? The main problem is that in every turn we bet an entire amount of money, because of which we can intuitively see that as we lose money, we can gain less and less with every win. But as we win money, we can lose more and more with every loss. At the same time, I would like to point out that the case with equal number of heads and tails is the most important case here, because it is the center point of a distribution. It is both the median and the mode. And if this case gives us a net gain, more than half the players will gain money, and vice versa. So this is the case that we would be going to focus the most. Um, in fact, as the number of tosses approach infinity, for most players, the number of heads and tails will also approach to near equality. And so most players will approach this case where they will end up losing all of their money as the game proceeds. In fact, because here a small session of players make a big amount of money, and because the total loss is bounded, the average gets skewed heavily, and that's why we see the weird uh, average net gain as was shown in the previous slides.
Is the total amount of money in the system more than before?
Yes, yes, it is. That's why the average is more than 100.
So what is the problem exactly? The belief that playing more increases winning chances is false, as each toss is independent. This creates a paradox where continuing to play increases the risk of losing everything. In fact, when you start playing locally, you feel like every move is profitable, but on a global view, it is not. In fact, on continuing to play the game at a very high number of tosses, you will be ending up losing the money. Hence, this explains why gambling is addictive and the gambler ends up saying just one more game and hence loses money.
So it now seems that gambling is a very bad thing to do, and you should not gamble at all. But we'll not ask you to not gamble. Instead, since we are from ISC, we'll use some math to show you that this game can be made profitable if we are a bit more thoughtful.
So, what if instead of putting the whole money at stake, what if we put a fraction of that particular money at stake? So, it seems the gain in the median is 1 plus FA1 minus FB, where F is the fraction of the money that we will be investing, and A is the gain in wealth, and B is the loss in wealth. And here, FA is the effective gain, and FB is the effective loss. Particularly, we are focusing on the median case just because, as Mrigank discussed before, median case is the deciding factor here. And hence, we would like to see what is the gain in the median case. And here, for this particular expression, we have taken the case of one head and one tail. And the other such cases would be nothing but the powers of this particular expression. Let us visualize it. Here you can clearly see that.
Why do you call median case?
Okay. Go to the
So-
graph part.
The graph.
No. That only work. Visualization.
This,
Yeah. You can show you.
yeah. If we plot, I mean, most. So if we see which players gain how much money in that.
Equal numbers.
Yeah.
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 The deciding factor, like if we visualize it like 3x, it is the median case and mode case.
If you like sort all of these amounts,
So here in the graph, you can clearly see that when the fraction is 1, the value is less than 1, and hence we are losing the money. And at 0.375, the value is greater than 1, and hence we will be gaining the money. And in fact, this 0.375 is the optimal fraction by which you need to invest to have the maximum profit again. This is
it's that expression which we showed on the
This is the R. Yeah.
This is so much you
Yeah.
The
The y-axis models the median case.
Obviously.
Is there a question there? Yeah, that's a good question. If you change the value of A, this graph will also, it will also change, of course. For some values of A and B, like if B is very small, B is the loss here. Every game gives us a profit in the long run. For some values of A and B, it can also be the opposite. So yeah, this can very well be varied, and we'll have different optimum points for different values of A and B. So this is 1 plus XA is the case for one heads. When you gain XA fraction of money, X is the fraction that you bet, and A is the profit percent. And 1 plus XB is for the cost. So because we want to model the median case, which is the case for particular number of heads and tails, every such case will be a power of this expression, this squared, cube, and so on. So yeah.
Any other question?
Okay, we'll probably proceed.
Go to slide number 21. So now that we know, we can find the optimal fraction here, and this can be generalized. And in fact, it has been generalized by Kelly, and it is called Kelly criteria. And it has been used in multiple ways in investment, trying to find out the optimal amount to invest in a particular stock or investment. So hence we can conclude that dividing your money to invest in asset is the very right decision.
maybe there's a way of saying it. Don't put all your eggs in one.
Yeah.
Yeah. don't put all of your money into one particular investment.
So, but what happens to the rest of the money? Do you put some fraction of the money in this
No,
gambling
no,
thing?
you can add it later.
Is
The
it-
rest you
yeah,
keep-
you're
yeah.
keeping on
The model will
reinvesting,
get complicated, like it will be complicated to keep on adding, but that will end up giving the
for example,
maximum.
suppose
The
your
fraction
bet
is
was-
like-
bet was 50% or whatever. So you put 50% of the money in the first chance.
Yes.
And then what do you do if it's a head or a tail? Then
If it's a heads, then you give it to 180. Sorry, you give
Yeah,
it to 50 times 1.8.
use again the optimal.
Yeah, and use it in the entire sum.
So it's a dynamic.
Yes.
Yeah.
The F is dynamic. I mean, the fraction is that the absolute value of fraction is dynamic. So I hope that from this paradox you learned that you must do your math before you invest or well gamble. That is your choice.
I have a question. I don't think the F is dynamic.
F is constant, but the absolute value of the money that you put in.
That will be, but your F, the fraction that you put,
Yeah.
is constant.
Yes.
Fraction.
Yeah.
Depending
The
on how much.
money.
Thank you. So that
Thank
was,
you.
I have an interpretation. Yeah, first.
Yeah.
So actually what you're looking at is, let's say that you have an initial endowment of X. So you're looking at a fraction. I'm trying to come up with the reason for why that product is a good one.
Yeah.
So if you look at each stage, what you would get. If you think of success or failure as 1 or a 0, you can write the gain at the end of n time steps as 1 plus, let's say, a raised to the power xi, where xi is at the right stage. If you're successful, this will be active, times 1 minus b to the power 1 minus xi. And when you actually run this for long duration, when you look at this, those exponents will be 1 plus a summation of the xi, and then 1 minus b summation of the 1 minus xi. 1 minus xi, all the ones give you a 1/2 in your example, for example. But then the other ones you could accumulate. We have a 1.8 divided by 2. So actually, if you apply the law of large numbers to the exponent, that's what Kelly's principle also looks at. You should be looking at 50% on very high probability. The growth rate is actually given by 50% plus or 50% minus. That's the reason why you're looking at the product.
just to point out again, as the player keeps on playing and becomes like approach infinity, they will all like eventually approach the case where they have like nearly equal number of exit games. So that's where we are trying to do that case.
Yeah.
So if you just put all the money, then what happens to the expected winning? It goes to infinity in this way.
So the average will tend to infinity, but the median will just tend to 0. It will get worse and worse.
Yeah.